Good, folks. And I tell you what, before we respond to any of these questions, I have 3 pieces of bad news for you. Each one worse than the one before.
Oh, nice.
The first piece of bad news is that we have to end class early today. We can only be here for 30 minutes.
Oh my God!
The second piece of news, which is worse, is that was a joke.
Oh,
Yeah.
I'm sorry.
We're staying here the whole time. I'm sorry, Simone. I've never pulled that one before, and I thought, man, I gotta try this.
Oh my
Yeah,
And then the worst news is that a singular dice is not a dice, it's a die. Yeah, so a single dice is not even called a dice, it's called a die. Isn't that weird? And then plural is dice. And the really weird thing there is that in the original French, the S at the end made it plural, and yet we insert the C at the end. If you really wanted it to be plural in English, it would be more like dies, like an old person. But no, it's D-I-C-E. Okay, so again, sorry about that, Simone. I just thought, hey, what the heck? This would be fun. All right.
That was your joke of the day.
That was my joke of the day, folks. You just heard it. I don't have to erase. Oh no! What just happened?
Karma's
No, it's still there. I just hit something. It better come back on.
Oh, it's still gone.
No, it'll come back. Boy, I'm in real trouble if I. No, it's gonna come back. That was almost, what do you call that? A self-fulfilling prophecy. That was almost a self-fulfilling prophecy. All right. So, how do we calculate probabilities? So the first question was, if you have a single dice, which should really be a single die, but most people don't understand that die is the singular of dice. So I just say dice anyway. In modern English, we for the most part mean dice. It has one or many. What is the probability of rolling a 5? So
1 out of 6.
yeah, what's the probability of rolling a 5?
1/6.
Just 1 out of 6. Now, why is that the answer?
So there's only 1 5, and then there's 6 numbers.
Yeah, exactly right. So what the denominator here is called the sample space. So that's all the possible things that could happen. And so when you roll a dice, all the things that could happen are the numbers 1, 2, 3, 4, 5, and 6. Whereas what you actually want is just to roll a 5. And so there's only one of them. And so you just count up how many things you have in the numerator, you count up how many things you have in the denominator, and your probability is 1 in 6. So that's it. What's the probability of rolling an even number?
3 6.
Yeah, how many even numbers are there? 2, 4, and 6. So it would be a probability of 3/6, which you could, of course, simplify, and so that's 1 and 2. And of course, you can always just rethink the problem. Like 1 out of every 2 numbers on a dice is even, and 1 out of every 2 numbers on a dice is odd. So that works anyway. What's a composite number?
A number that's divisible.
Yeah, so like in terms of composites, just so we have these definitions, because we'll see a lot more examples like this today, a prime number is not divisible by anything. So 2, 3, 5, 7, 11, 13. Whereas a composite number is divisible by something other than itself and 1. So for instance, 4 is divisible by 1 and 4, but also by 2. And 6 is divisible by 1 and 6, but also 2 and 3. And 8 is divisible by 1 and 8, but also 2 and 4. So those are composite numbers. So 9, 10, 12. Does everyone feel okay with those definitions for prime and composite?
Yeah.
Okay. 1 is neither. 1 is considered the unit. It's kind of weird, but in number theory and mathematics, we don't actually consider 1 to be prime or composite. It's a special third class of number called the unit. Okay, so what's the probability of it being a composite number?
Third.
Yeah, only 4 and 6, right? So only 2 out of 6 numbers, so that's a third. So 2 out of 6 numbers are composite, which simplifies down to 1/3. Okay, and then what's the probability of rolling a 7? Yeah, that one's kind of clever. There's 0 ways to roll a 7, so 0 out of 6 is 0, which means it's impossible. If you get a probability of 0, that means it's impossible. It cannot happen. Okay, what about if you have a pair of dice? What's the probability of rolling a pair of 6s? And for this, I will show you the sample space. This diagram here is called the sample space for rolling 2 dice. So you have a red dice and a green dice. And what's the question? What's the probability of rolling a pair of 6s? So first of all, how many items do we have in our sample space?
12.
How many different events could happen? So if you roll 2 dice, how many different ways can that happen that you roll 2 dice? Yeah, 36. You've got 1, 2, 3, 4, 5, 6 going across, 6 going up, so that's 6 times 6 is 36 different possible rolls of the dice. Now you'll notice that even though there's 36 possible rolls of the dice, that's a 2 and a 1, and that's a 1 and a 2. But we're considering those different, because that could be a red 2 and a green 1, or a green red and a green 2. So that is genuinely a different roll of the dice. So anyway, what's the probability of getting 2 6s?
12.
Not a 12.
136.
Yeah, there's only one way to roll 2 6s, and there's 36 possible ways to roll 2 dice. So the probability of rolling a pair of 6s is 1/36. So that's the probability of rolling 2 dice, or a pair of 6s. What's the probability of rolling both odd numbers? Both odd numbers. Where do we see 2 odd numbers?
1 and 1.
You got the 1 and 1, 3 and 1, 5 and 1. So that's 3 so far. And then you've got, well, there's a 2 in all those, so those are right out. And then here you got 1 and 3, 3 and 3, and 5 and 3. So that's 3 more. And then these all have a 4 in it, so those are out. Here you got 1 and 5, 3 and 5, 5 and 5, so that's 3 more. Oh, I drew that one a little bit. There we go. And then these all have a 6 in it, so they're right out. So how many total pairs did we have with just odd numbers?
9.
9. So that'd be 9 out of 36, which is
4.
a 4. That's pretty interesting. That's pretty interesting that you can use a pair of dice to create an event that has the probability of 1 and 4. Because, I mean, if you look at a single dice, you're looking at a probability of 1 and 6. And yet, by having 2 dice, you can create an event that has a probability of 1 and 4. I wonder, could you create an event whose probability would be 1/3? I'll make this easier. Could you create an event where the probability is 1/2?
Yeah.
What would happen 1/2 of the time? Well, I don't know. What would happen 1/3 of the time?
Rolling 1 dice that's an odd number.
Oh, just rolling a single dice that's an odd number? Oh, like if the green dice is odd.
Yeah.
There you go. That would be a probability of 1/2 because the green dice is only going to be odd here, here, or here, and that is successfully half of the sample space. So yeah, that would work. What about a 1/3? Can anyone come up with an event that would happen 1/3 of the time? That's kind of tough. Keep in mind that's 12 out of 36. So what would happen 12 out of 36 times? Oh, I've got one. It's kind of cheap. What if you roll a dice and the green dice is a 5 or a 6? The green one has to be a 5 or a 6. Then that's just this column or this column, and that's 12 total cases out of 36. And that would give you a probability of 1/3.
Works.
Does it work? Yeah. Okay, so some more questions. What is the probability of both odd numbers? We already did that. Wait, did we already do that? Yeah. What about a sum of 2? How many ways can you roll a dice and get them to add up to 2?
Once.
Yeah, just this one. So that probability is, again,
1 out of 36.
1 out of 36. There's only one way to do it. What about adding the dice up to 7? How many different ways can you add the dice up to 7? Where are those possibilities?
4 and 3.
Yeah, it could be a 4 and a 3, which is also 3 and a 4.
5 and 2.
You got the 5 and the 2, or the 2 and the 5.
1 and 6.
Or the 1 and the 6, or the 6 and the 1. So those are all the different ways that you can roll 2 dice and they would add up to 7. And how many are there? 1, 2, 3, 4, 5, 6. And so that's 6 out of 36.
1/6.
Which is still, yeah, 1/36. I'm sorry, 1/6, yeah. So the probability of rolling 2 numbers to add up to 7 is 1 in 6. Okay. These are all just some basic examples of using a sample space to compute probabilities. Now, I think what would be really hard would be to come up with something that was 1/5. Is there an event that you could say would happen 1/5 of the time?
No.
Is that possible that you could create a dice event with 2 dice that would only happen 1/5 of the time?
5 doesn't go into 36.
Yeah, 5 doesn't go into 36. So if you wanted that to be a 5 in the top there, there's just no way to do it. It would turn out to be a decimal. So that'd be like times 5 times 6 times 7. Yeah, it'd be like, you'd have to multiply times 7.2. So 1/5 would be 7.2 out of 36, but you can't roll the dice, or you can't find 7.2 combinations. So 1/5 is literally an impossible probability to build using dice. Or using a pair of dice, anyway. Okay, I think I had maybe a couple more sample questions here. How many ways can you flip a coin 3 times? Now this one, I actually want you all to take out a sheet of paper, a sheet of lined paper, and write down all the ways that you can flip a coin 3 times. So go ahead, take out a sheet of lined paper. Yeah, don't do it on the packet because I don't think, well, unless you just want to flip it over, you can do it on the back. Flip it over and do it on the back. How many ways can you flip a coin 3 times?
I don't understand your question.
So like for instance, it could be heads, heads, heads. Like if you just sat there and you go flip, 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 what'd you get?
Okay.
So one possibility is you could do head, head, head. And if you want to start with an easier problem, you could say, how many ways can you flip a coin twice? Right, so I'll demo that one. If you just flipped a coin twice, it could either be head, head, or it could be head, tail, or it could be tail, head, or it could be tail, tail. So that's how you flip a coin. How many ways can you flip a coin twice? Whereas right now we're asking, how many ways can you flip a coin thrice?
I got 6.
There's a couple more.
Is there more?
Uh-huh.
I can't think of
How many did you get?
There's one more.
How many did you get? You did? You got 7 on your paper?
Yeah. There's one more. Yeah, I got 7.
There's one more.
I think you're lying.
I very rarely lie.
Well, you just lied earlier. So.
That was a joke. Huge difference between a lie and a joke. The main difference is who you are. If you're the person telling the joke, it was funny, but if you're the person hearing the joke, then that you might call that a lie.
I agree.
I can't figure out the 8th.
I did mess with your emotions.
So is this
What
supposed
is
to be
it?
8?
It is 8.
Oh, okay.
Yes.
Okay.
Simone, did you get it? Oh, you got 9s? Okay,
Heads,
very good.
heads, tails.
I heard a 6, I heard
Heads,
2
tails,
7s, I got an
heads.
8, and I got a 9.
Tails, heads, head.
Oh, yeah, yeah.
Tail,
yeah,
tail,
yeah.
head.
I'm
Tail,
sorry.
tail, tail.
Yeah.
Tail, head, tail.
You have heads, tails, head. Heads, tails, head.
Yeah.
Yeah.
Now I have 7.
3, 4, 5, 6, 7. I have 7.
So you got triple
Tails,
head,
head,
eight, I mean head, tail,
head.
You only said, so I wonder which one you're
head,
missing.
tails, head,
Well, here's the way to
tail,
think
tail,
of it.
tail,
I see that you have a
tail,
T
head, tail.
in the front of 4 of them.
tail,
You
tail,
don't have an
head.
H in
tail,
front of 3 of
tail.
them.
Oh, no, no, no.
So by symmetry,
I don't
there's
know.
like one more with an H.
I'm so over it. Like, I don't know.
Yeah.
But so
Oh, yeah. Oh, you got that
I only
one
got
twice as
7.
well. So you have 6. Yeah, and you have 7. Now, for instance, you
You
have
have
a
to read them out or pick your heads up.
You have an H 3 times listed.
Heads, heads,
You have a
heads.
tail 4 times.
Heads, heads,
So you
tails.
should have another H.
Head, tails, head.
If it's going to be symmetrical,
Oh, yeah.
which it should be symmetrical.
yeah.
Heads, tails, head. Heads.
Heads, tails, tails. I'm filling the next.
Oh,
head.
that's the one I'm missing.
Now notice, 1, 2, you have 4 tails to start. You only have 3 heads to start. So you need one more head.
I'm kidding. Yeah, I like,
Hey, how'd it go? Oh, you got it. Oh, at least I think it's just a quick check.
Yeah. No, I'm the class. I mean,
And then,
I just saw it.
I mean, you've got 1 H, 3 H's, but you have 1, 2, 3, 4 tails. So you need one more H in the front. So it has
Yeah.
to be H.
Oh,
Did you find a bucket? Oh, good.
Yeah, but not for like not because I don't listen.
Yeah,
Okay.
because then you would know.
So let's compare answers and let's see if we can be systematic about this. Because systematic is very helpful if you can do it. So first of all, how many ways can you flip a coin twice? I'm sorry, just once. How many ways can you flip a coin once? Yeah, I mean, you either flip it heads or you flip it tails, right? So that's it. If you're just flipping a single quarter, there's only 2 ways to do it. It's either heads or tails. So if you want to flip it twice, what you basically say is that you see that combo, HT right there? Well, you could either roll heads first and then flip HT, or you can flip tails first and then flip HT. So do you see what I just did there? I took the HT that I had already come up with, and I made that the second roll, and I preceded it by either flipping heads or flipping tails. So now I could do that trick again. I could talk about flipping a coin 3 times in a row. And what I'm going to do now is take this whole chunk here and say, well, I could either roll a heads first. So it's going to be 4 entries. So it's heads, 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 heads. And then I put all of these entries right here. So it'd be HH, and then head tail, and then tail H, and then tail tail. And now I'm going to do the same thing again, but now I've preceded it by all tails. So now again, I put in the HH, H tails, tail heads, and tail tail. So do you see what I just did? Because that takes all the guesswork out, right? It's just a matter of throwing in this pattern and doing it again. So how could I flip it 4 times? Do you see what we would do?
About 10.
About what?
10 times.
10 times? More than that, because here we have 2, then 4, then 8. 2, 4, 8. What would the next one be? 2, 4, 8. How's that pattern going? And look again, see, I take this pattern right here and I list it twice. And then I took this pattern and listed it twice.
16.
So every time I'm multiplying times 2. So yeah, if I flipped it 4 times, there'd be 16 possibilities. Basically, I'd take all these entries and I'd write them all down with a tail in front, or with a head in front of each one. And then I'd write them all down again with a tail in front of each one. And that would give me all 16 entries.
32.
So yeah, then the next one would be 32. Okay, now that's just one way of doing it systematically. Another way of doing it systematically is to make a branching tree. And maybe you've seen this before. So I'm going to start, and I'm either going to flip tails or heads. I'm going to put heads or tails. Now, so that's my first coin flip right there. Is I just flip it, it's either heads or tails. Then I flip it again. And so then again, I either go heads or tails. And from here, I either go heads or tails. And right now, if you just follow the lines, that's going to be HH, or that'll be HT, or that'll be TH, or that'll be TT. And then I can flip a coin a 3rd time, and each one of these I could branch again. So if after flipping that one, I could flip HT, or after flipping that one, I could flip HT, or after flipping that one, I could flip HT, or after flipping this one, I could flip HT. Now look how nice this is, because now what I have is just a branching tree, and I can follow each possible branch out to the leaf and just write it down. So that'd be H, 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 and that's one possibility. Or I could go HHT, and that'd be another possibility. Or I could go HTH, that'd be another possibility. Or HTT, that's another possibility. Or I could go down here and go THH, or THT, or TTH, or TTT. Okay, so just curious, who liked the branching tree method or this method? Like, who liked this method? This way? Maybe another one of you? Okay, who preferred the branching tree method? Maybe just a couple of you. Who prefers no method? No, I'm just kidding. Okay, so what we just looked at is a lot of different ways to count things. And in fact, that's what chapter 7 is, counting things. Right? The whole chapter is going to be about how do you count how many different ways something can happen. And these are just a couple of the basic tools that we have at our disposal. So chapter 7 is about counting and it's about probability, which is very different. We won't be doing any matrices in chapter 7. Right? We're all done with matrices. We're all done with row operations and inverses. I know you're all sad about that.
Yeah.
Yeah, but we are done. Okay.
But then we see them on the final again, right?
Yes, you'll see them on the final. Now, by the way, everyone, are you familiar with a deck of cards?
Yes.
Has anyone ever not? Are you like, I've never played cards? Luis? Really no? Okay, I wasn't sure.
I mean, unless you would have counts.
Uno is a game of cards, but it's not this deck of cards. So, folks, how many cards are there in a deck of cards? How many cards are there in a deck of cards? First of all, what are the cards? It goes ace, so the A stands for ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it goes
11.
Jack, queen, and king.
Yeah, Jack,
yeah.
Queen, King. I mean, you can consider it 11, 12, 13. That's
Sorry,
fine, because
I
they do go in order. They do go in order. It has to be 10, Jack, Queen, King. Yeah. So you've got, how many total cards is that then? In just one row, how many?
13.
13. So you've got 13. And then you have 1, 2, 3, 4 different suits. These are called suits. So you've got hearts, diamonds, spades, and clubs. So you've got 13 times 4, which is?
52.
52. Same as the number of weeks in a year.
Wow.
So the number of cards in a deck and weeks in a year, they're both 52, and they're both divisible by 4. Right? That's a good thing, right? Because years can be split into quarters, right? So when you split a year into quarters, you've got 4 quarters of 13 weeks each. And that's what this deck of cards is 4 quarters of 13 weeks each. Which is weird because how many months are in a quarter?
3.
3 months in a quarter. And how many weeks are in a quarter? 13. So a lot of times we think that a month is 4 weeks. And if you have 3 months of 4 weeks each, that would be 12 weeks. But there's really 13 weeks in a quarter. So there's really 4.333 weeks in a month. In any case, that's a deck of cards. So I just want to make sure everyone's familiar. How many of the cards are red?
2.
Oh, 2. How many of them? Half. Yeah, 26. 26 of them are red. How many are black?
26.
26, or half. So that's right. And then what fraction of them are hearts?
152.
What fraction of the whole deck is hearts?
13 out of 13.
13 out of 52, which simplifies down to
1/4.
1 out of 4. Which should be obvious because there's 4 suits, and so hearts is 1 out of 4 suits. So you can say that hearts, the probability of drawing a hearts is 1/4. Probability of drawing a diamond is 1/4. Probability of drawing a spade is 1/4. Probability of drawing a club is 1/4. What's the probability of drawing a king? 4 out of 52. Which, what's 4 out of 52 simplified to?
1/13.
Yeah, 1/13. Right? Because when you think about composite numbers, so a composite number such as 52, there's only one way to break it down, and that is 4 times 13. So if you take 1/4 of 52, the answer is 13, or 1/13 of 52 is 4. So you have a 1/13th probability of drawing a king. You have a 1/13th probability of drawing an ace. You have a 1/13th probability of drawing a 4. Whereas you have a 1/4 probability of drawing a heart, and a 1/4 probability of drawing a club. Okay, yeah, so that's a deck of cards. Does anyone know when cards were invented? Like these cards?
1895.
John's making it up.
Probably Larry.
It's got to be around a little bit longer than that. Let's see. Because they've been playing cards for a while. When were cards invented? And by that I mean this deck of cards. There's lots of card games going back to 1000 AD, but
I was close.
where's the yeah, what's a standard 52? China had some form of cards. They had some form of
It
cards.
said 1300 in Europe.
Modern deck formats. I don't see a year in there. There's that. I still don't see a year in there. What the heck? You'd think that they would have a year. No.
Right there.
The invention is attributed to French in 1745. The first such pack of Latin suits was printed in 1693. So let's say the 1700s. That sounds about it. So since the 1700s, we've had this standard deck of playing cards right here. So that's what I was just showing you.
It's only off by 100.
So you get, yeah, you were pretty close there, though. So ace through king, and there you have it. And a standard deck also comes with 2 jokers. You have 2 jokers, but we don't traditionally calculate probabilities using jokers. That would be out of 54.
What is that?
That we don't calculate probability using jokers?
Oh, because it wouldn't be even split, right?
Well, that's true, because it certainly does throw off the probabilities, but also because jokers aren't used in every game. Usually jokers are only used in certain games.
Spades.
Is it what? Spades?
Yeah.
What do you mean in spades? Oh, in spades you use jokers? Oh, okay.
Shut up.
Okay, so folks, this right here, what you're looking at, this is called a sample space. It's all the possible things that can happen in a deck of cards. And this is called a sample space of rolling 2 dice. And yeah, that's what I got so far. So today take a look, folks. This is very exciting. We have chapter 7, 8, 9, and then
Oh man, we're almost done.
yeah, we are almost done. And I don't believe that there's a padding day for chapter 7, 8, 9. So we have to finish those final exam, and then we have the final exam. So your due dates are still 2 class periods after we do it. So if we finish chapter 7 today, it'll be due on February 26th. And I already told you a joke, but I put 4 jokes here, so I can do 2 jokes today and 2 jokes on Thursday. So here we go. Sometimes I tuck my knees into my chest and lean forward. That's just how I roll. Okay, what's a pirate's favorite letter? A. Arr. I mean, there's a lot of different ways to say the answer. A. You can say R or the C, or maybe I. See, there's a lot of letters. I told my daughter this joke, and I was asked her, what's a pirate's favorite letter? And she says, R. She says it just like that. All right. So here we go. Chapter 7 is sets and probability. So, everybody ready?
Wear cards and
You want some?
Because you asked how many red cards there are, and he said 2.
Maybe he was thinking about the jokers. After all, you're all a joker.
I was gonna say it too, like, it took too long, so then you said it and laughed.
Wait, wait, you thought there were 2 cards in the deck?
I was gonna say 2, like, that just popped into my head. You said it before me, and someone laughed, so I did it.
I know, swear, that's why I always keep my mouth shut.
Yeah. I'll start doing that from now on.
All right. Folks, you have a lot of good, positive, giggly energy today. You must be so excited that we're done with matrices.
Yeah.
There must be it. All right, well, here we go, folks. Up at the top, I want to give you some notation first. So we're just going to do some definitions. And then we'll move on and actually try some example problems. So in set theory notation, when we make a set of numbers, we build it like this. So let's say that I want a set of numbers from, the set of numbers in a dice. So you write down the set bracket notation, 1, 2, 3, 4, 5, 6. So that's how you build a set. You use curly brackets, and then you just list off the elements. So these are, I'm going to label it numbers on a die. That is the singular of dice. So the numbers on a die. So that would be our set. And if we want to say that a object is an element of a set, we use this symbol right here, which looks like a little E, but it's very curvy. And so you can say something like 2 is a member or an element of the set. Now let's call this set something. We're going to call this set A. So we would say 2 is a member of set A. And the member symbol is basically a curve with a line through it. That's how you can draw it.
So it's like a C, it's like an E.
It's like a C with a line through it. Yeah, that's a good way of saying it. So if we're calling that our set, that's set A, we would say 2 is a member of A, because 2 is in that set, but you'd say 7 is not a member of A. So we're just saying whether something's in the set or not in the set. Okay, so that's numbers on a dice. And that's my first set. What if, let's build another set. And golly, what would another set be? How about, I don't really have another natural set off the top of my head. So we're just going to arbitrarily make one up. And we're going to call it the set of numbers, the even numbers from 1 through 10. So the even numbers 2, 4, 6, 8. Actually, we'll just say 2, 4, 6, 8. That's my other set. 2, 4, 6, 8. Who do we appreciate? So there's my other set, set B. So I've got a set A, which you could say is the sides of dice. Set B, which is the first couple even numbers. And so again, I could say something simple like 6 is a member of B, but 10 is not a member of B. Now these sets, we're just making them up, right? A set can be anything. You can put anything you want in a set. It doesn't even have to just be numbers, but for the most part, it'll be numbers in this class. Now, so let's talk about, that's just using the symbol element. That's for an element. The element symbol is that one. What about subset? That symbol is a C with a line underneath it. So now I could say a subset means just some number of those and build another set out of it. So if I wanted to, I could just take the set consisting, so right below my set A, I'm going to make set C to be just the numbers 1, 2, and 3. So now I've got set. So now I can say that C is a subset of A. Now what does this mean that C is a subset of A? It means that everything in C is also in A. And so if you look, C has the numbers 1, 2, and 3. All of those are also in A, so I would say that C is a subset of A. And if you want to write that out, everything in C is also in A. So C is a subset of A, and hopefully that's what you would think the word subset would mean. Whereas, for sure, I could say 2, 4, 6, 8, B is not a subset of A. Because everything in B is not also in A. So that's what subset means. And then finally, we have these two other ideas called union and intersection. Union, I'll do this one first. Union means anything that is in either set. So union means either. So if I said A union B, that would be the set consisting of any element that's in either one of them. So that would give me all the first numbers from A, 1, 2, 3, 4, 5, 6, as well as anything else that's in B. I already have 2, 4, and 6, so I can include 8. So when I say A union B, it's going to be a larger set which contains anything that's in either A or B. And that's what union means. Union means it's in either one of them. And the symbol is the letter U, literally U for union. Whereas when we talk about an intersection, we use an upside down U, A intersect B. And that means anything that is in both simultaneously. So to be in the intersection, it has to be in both of them. So what's in both A and B? Not 1. Oh, 1 is only in A. 2,
6,
6, and 4. 2, 4, and 6 are in both. Okay, yeah, so for union, we use the letter U. Intersection is the upside down U. And that's just a real quick look at what these definitions state. Any questions on just those definitions? Keep those out in front of you so you can see them. So let's just do some examples. Is 7 an element of that set?
Yeah.
No. No. That's false. 7's not actually in the set. 7 divides all those numbers, but that's not what we're talking about. This curly bracket notation literally means we have a set of numbers, 14, 21, 20, 35, 42, and 7 is not one of them. So that's false. Now what about 3? Is it true that 3 is not a member of that set?
Yes.
Yeah, that's true. It is true that 3 is not a member of that set. So that might feel a little bit of a brain twister there. We're just asking, is this statement true or false? And this statement is true. 3 is not a member of that set. And then finally, looking at number 3, another way of building a set is you start by using a curly bracket, and you say, my set consists of all numbers x such that, that's what that vertical line means, x is an even counting number, such that x is between 8 and 14. So let's look at that first, because that's what they're talking about. I want to build a set of all the numbers x, such that x is an even counting number between 8 and 14. So what are all the numbers in that set? What are all the even counting numbers between 8 and 14?
10.
Yeah, 8, 10, 12, and 14?
Yeah.
Yeah, that's the set we're actually talking about. So if you look at the set notation on the left, they're saying I want the set of all numbers x such that x is an even counting number between more than or equal to 8 or less than or equal to 14. So that's the set. And what they're saying is it true that that set is the same as the set of just 8 and 14? No. That's false. So right now you might be thinking to yourself, well, what's happening? What are we doing? We're just checking to see that we know how to read this notation. So on the left-hand side, they described a set that actually contains the numbers 8, 10, 12, 14. On the right-hand side, they gave you the set of just 8 and 14. Those two sets are not equal to each other because this set has more elements than that set, so this whole statement is false. Now, have you ever worked with set notation before? Curly brackets?
Yes.
Just curly brackets? Maybe you have, maybe you haven't. The curly bracket thing is just a way of building a set. And we're going to see a lot of different ways to build a set with various. We concretely count how many objects in the set and say exactly what they are. And once we figure out how to talk about sets, then we can start counting things in them, and then we can calculate probabilities. So how about these next couple problems? Is 579 a subset of 45679?
Yeah.
Yeah, because everything in here is also in here. You got 579, there's 579. So yeah, that set is a subset of that set. What about, is 5, 6, 7, 8, 10 a subset of 6, 8, 10? No, it's not a subset. Because everything in here is not also in here. So this is a subset of that, but this is not a subset of that. Okay, now here we go. Here's a nice example. They're telling us to let set A be 1, 3, 5, 7, set B be 5, 6, 7, 8, set C be 5 and 8, set D be 2, 5, 8, and let U be 1, 2, 3, 4, 5, 6, 7, 8. Now, first of all, folks, notice that this U is different from the U that means union. This U is just referring to a set, and in fact, this U means universe. This is the universe. So basically, these are actually all the elements that we're considering in our universe, and each of these sets over here is a subset of the universe. So A is a subset of U, B is a subset of U, C is a subset of U, D is a subset of U. U is our universe of all possible things, and then we've just built a few little subsets over here. So in this example, I could go ahead and state A is a subset of U, B is a subset of U, C is a subset of U, and D is a subset of U. That's the nature of U. U is the universe. You are the universe. Thanks. Okay, now what about C as a subset of D? Is that true? It's helpful to write it out. Is the set of 5 and 8 a subset of the set 2, 5, and 8? So is that true in part 6?
Yes.
Yeah, because everything in here is also in here. So 6 is true. Now what about this next statement? Is it true that C is not a subset of B? Again, this hurts the brain a little bit. So let's look. C is 5 and 8, and B is 5, 6, 7, 8. So looking at those two sets, in fact, it is a subset. So to say that C is not a subset, that's false. Okay, so what have we done so far? We're learning some new language, we're learning some new vocabulary, and we're looking at statements, and we're saying whether or not they're true or false. Which I'm sure everyone is like, this is really exciting. Like, I cannot wait to write home about this one. In fact, I'm already texting my friends. We're talking about set notation. It's labeling things as true and false. And it's so exciting. Okay, well, let's keep going. We're learning a new vocabulary. So how about here? Number 8, it says decide whether the statement is true or false. So is that set intersection with that set equal to this set? So first of all, what does intersection mean?
Both?
Yeah, intersection means both. I should write some of this stuff down over here. So U is union, which means either. Whereas upside down U is intersection, which means both. Now, what is helpful is to work out the left side and work out the right side. So on the left side of the equal sign, what elements are in both?
3 and 9 is 6.
What elements are in both sets? Just 3 and 9. 3 and 9 are in both sets. Whereas on the right-hand side, we have the set 3, 6, 9, 12. And is that set equal to that set? No. that's false. Okay, and then what does U mean again? Union? Yeah, union means either. Now, union, you might think about a marital union. When two people get married, then what they own together is what either one of them owned. And that's kind of like this. In a union, you just get everything that either of them has. So the union of these two sets would be 6, 12, 18, 24. Which indeed is equal to 6, 12, 18, 24. Okay, so that one's true. Ooh, new notation. We didn't see this one yet. See this little circle with a line through it? That is the saddest set. A circle with a line through it is a set with nothing in it. I mean, isn't that sad? You almost want to cry for that set. There's nothing in it. And so we call it the empty set. You can also call it the null set. There's nothing in it. You'll notice that this, like if you went to solve an equation but there was no solution, you might have used that symbol to represent that there's no solution. And that's because the set of solutions to an equation, there was nothing in it, so they called it the empty set. So what does this problem really say? The set 13, 2, 9 intersected with the empty set. What is that? What element is in both of them? Is there an element that's in both sets? Nothing. So the whole left side is the empty set, and the right side is still 13, 2, 9. And that's not true. That's false. Those two sets are not the same.
Can you re-explain number 9 for me, please?
Yeah, sure. Union means write down anything that's in either of them. So you take the union of 6, 12, 18, 24, and 6, 18, you write it down if it's in either one. So basically, I get to write down anything from this set and anything from that set. But this set only had numbers that this one already had. So, did that answer your question?
You did, yeah,
Okay,
it clicked. Thank you.
great. Okay, so far we've done sets with numbers in them, but we can also do sets with letters in them, which equates to the same thing. So there's a little bit more terminology here. First of all, notice that you have the universe again. So this is kind of the largest set that we're considering. This is our universe. And it has the letters Q, R, S, T, U, V, W, X, Y, Z. Q, R, S, T, U, V, W, X, Y, Z. Yeah. So it's the end of the alphabet. I had to sing it. All right, so that's our universe. And then set A is just the letters Q, S, U, W, Y. B is Q, S, Y, Z. And C is all those. Okay, so we have one more notation that we have to think about. And that's this little apostrophe. So what does this B apostrophe mean? Well, first of all, we can pronounce that B prime. And what it means is everything not in B. And by that, we mean everything in the universe that's not B. Another way of saying it is B complement. Complement is actually the real word for it. B complement. And it means everything in the universe that's not B. So how can we actually list the elements of everything in the universe that's not in B? I want everything in the universe that's not in B. How would you do it?
R, T, U, V, X.
How'd you come up with your list, Bata? How did you come up with your list?
I just see the universe up but not in.
Right, the universe, but not in B. So what could we do to make it easy for our brain, folks? Q, S, Y, and Z. Can we just come over here and cross it out? Q, S, Y, and Z, and everything that's left. So that'd be R, T, U, V, W, X. And that would be B complement. Does that work? That's everything in the universe that's not B. And the word is complement. Not compliment, like you look really nice today, but complementary. Okay, so B union C, we've already seen a problem like this, but B union C, again, you want to write it out very specifically and say, okay, well, B is Q, S, Y, Z, and C is V, W, X, Y, Z. And I want to write down their union, which is anything that's in either one of them. So if you see a letter in either of them, write it down. And what would probably be helpful would be to cross them out as you go. So like I used Q, here's Q. So again, in order, Q, R, S, I see an S, T, U, V, there's a V, W, there's a W, X, there's an X, Y, there's a Y, Z. So that's the union of B union C. It's everything that was in either one. Now, at this point, I totally can appreciate that you're probably sitting there and asking yourself, what is happening right now? Like, I was really excited we weren't doing matrices, but what is going on? Well, we're just learning a new vocabulary. We have a lot of new vocabulary now, where we have the union symbol, the intersection symbol, the empty set, the symbol like B prime, which means B complement, so everything not in B. So we have a lot of new language to talk about when is something in a set and when is something not in a set, and how do we talk about it. A intersect B prime. A intersect B prime. We'd want to first write down both of them. So what's A? A is Q, S, U, W, Y. And we're going to intersect that with B prime. Fortunately, we already wrote down B prime earlier. It's R, T, U, V, W, X. And now what do we want to do? We want to find the intersection, and that means we only write it down if it's in both of them. So what's in both of them? I would just start at one set and just check to see if it's in the other one. So Q, is it in the other one? No.
Just kidding.
Good kid. S, is it in both of them? No. U, is it in both of them? Yeah, so I'm actually going to write down the U. Okay, now that's gone. W, is that in both of them? Yeah. And then Y, is that in both of them? No. Okay, so now I'm done. I don't really have to bother now going over to check my other list because in theory, those won't be in the first one either. But you can check R is not in the first one, T is not in the first one, U was in the first one, but I already wrote it down. And V was not in the first one, W was in the first one, I already wrote it down, and X was not in the first one, so I didn't write it down. Yep. All of this notation that we've just used is all called set theory. And believe it or not, set theory is the axiomatic foundation of all known mathematics to all humankind. At the bedrock of all the mathematics that exists, it can all be boiled down to these set theory notations of using curly brackets, unions, intersections, empty sets, complements. It's what? Oh. So any questions on what we have so far? Sadai, how are you doing? Sadia? Any questions? Diego? David?
No.
Okay, Bata? All right. Well, let's keep going then. Adon, questions?
Good.
Luis? Simo? Josue? Michelle?
No.
All right. Okay, so now we start getting into something.
Go back.
I'm here.
Okay. I think number 12.
Number 12?
Yeah.
Oh, okay. Well, so set B is right here, and set C is right here. Yeah. And union means write it down if it's in either one. So I'm just going to make a set that includes everything that's in either one of these, and I'm going to go in alphabetical order. So Q, is it in one of them? Yeah, so I write it down. R, is it in one of them? No, so I won't. S, is it in one of them? Yeah, right there. T, is it in one of them? No. U. No. V.
Yes.
Yeah, V is right there. TUV. W.
Yeah.
Yeah. X.
Yeah.
Yeah. Y.
Yeah.
Yeah. Z.
Nope.
Yeah.
Yes.
So it doesn't matter that Z is in both of them. All you need is for it to be in one of them. Does that work, Michelle? Sure. Michelle, did that answer your question?
Explanations.
Did that work, Michelle?
Okay, you just, yeah.
Okay.
Because she was saying, because you were saying the letters that are in U, which she said is universe or whatever.
Oh, yeah.
So it kind of confused her because she was looking at just B and just C.
I got you. Oh, yeah. I was cycling through all the letters. But yeah, what you could have done, what you could do is just write down what's already in one set, Q, S, Y, Z, and then fill the other ones in.
Yeah, that's what I did.
Oh, that's fine.
I was remembering you were reading off the other letters.
Oh, I see. I see. I was just cycling through the alphabet, through the universe. Okay. Now, folks, now it starts to get a little interesting. We're thinking conceptually now. Here we have the universe is all soda pops. Now, what does that mean? It's in a can, or it's in a bottle, or from a soda fountain. I mean, I think we all know what's a soda pop and what's not a soda pop. Is orange juice a soda pop?
No.
No. Whereas Coke is a soda pop. So we're talking about soda pop. And then set A is all diet soda pop. So in A, we're just talking about diet soda pops. But what does diet mean anyway? No sugar. Yeah, no sugar, no calories. Okay, now B is all cola soda pops. What's cola? Cola is like Coke, Pepsi, RC, Dr. Pepper, but not Sprite or 7-Up.
Why?
Why? Cola is a dark brown flavor. Yeah, whereas Sprite, 7-Up, Mountain Dew, those aren't. Okay, C is all soda pops in cans. So that's just the ones in a can, not in a bottle, glass bottle, not from a soda fountain. And then finally, D is caffeine-free. So you see how we defined everything? U is the universe, it's all soda pop, which I suppose is just carbonated beverages. And then A is diet, B is cola, C is cans, and D is caffeine-free. So let's describe what these sets are. What's A intersect B mean? So first of all, what's A?
All diet soda.
Yeah, diet. And what's B?
Cola.
Cola. And so what does intersect mean? Both. So that means we're talking about soda pops that are diet colas. So that's it. It's got to be a diet cola. So that'd be a diet Coke, a diet Pepsi, a diet RC. Do they even make RC anymore? Is RC a thing? Does anybody even know what I'm talking about when I say RC?
Yeah. The RC Cola. Like
Yeah, RC Cola. Yeah, that was the thing. I realized that was probably a while ago. Let's see. Let's look at the picture.
Was it like Dr. Cola?
Oh, I remember Mr. Pibb. That was good.
Mr. Pibb's still around.
Mr. Pibb is still around. RC Cola. There it is. You all have seen RC before.
Yeah, they
What does
still
it mean?
make it. They still make
Royal Crown. Royal Crown Cola. Oh man, that was good. Mr. Pibb is my all-time favorite. Man, if I could have a Mr. Pibb right now. Why don't you? It's so good. What was that other weird soda? Is it Jolt? Yeah, y'all remember Jolt? What's another weird one? Anybody? Another weird soda? I don't remember. Anyway, those are all colas. What? Okay, so let's try another one. The next one says, ooh, now look at this. This is C intersect B prime. So that's telling us a lot. That's telling us two steps of information. They're saying first, look for anything that's in both C and B, but then look at everything else that's not that. So let's do C intersect B first. So what's C?
All soda pops and
Cans. Intersect B, what's B? Cola. So right now what we're talking about is cola in a can. So that's Pepsi, Coke, RC, Mr. Pibb. But then what they're saying with that prime mark is saying everything that's not that. So what we're saying is anything that's not cola in a can. Okay, so it's like you got this rule, like it's your moral system. I'll drink anything so long as it's not cola in a can. So that means you drink Sprite, Mountain Dew, or you even drink cola from a soda fountain. But you won't drink cola from a can. You're like, no, no way. I will not drink cola from a can. It's against my religion. But you'd feel free to drink something, a Sprite in a can. You could drink Sprite in a can. And you could drink Coke from a soda fountain, but just not Coke in a can. All right, wouldn't that be weird if that was like your thing? You roll up at a party, you're like, oh, do you have anything else? I don't drink Coke in a can.
There's a water hose.
Yeah, water hose, there you go. Okay, so what on earth is this? Now see, this is where it gets really exciting. What I can say now is we've built up our vocabulary and we're trying to know what that says. What does that say? So first of all, what's C? C is cans, but it's C prime, so that means not in a can. So not in a can. That's what that means so far. And then union, D, what's D? D is caffeine free. But then oddly enough, we're saying caffeine free prime, which means not caffeine free. Well, what does not caffeine free mean? Caffeine. It has caffeine, so caffeinated. And so union means either. So what are we really saying then? You roll up at a restaurant or a party, and they're like, hey, what do you want to drink? And you're like, well, do you have anything that's not in a can or just something with caffeine in it? That's what you just said.
So it can't be in a can.
Yeah,
It has to be caffeinated.
Yeah, I can't drink it out of a can because I cut my lips on the can. But I need something caffeinated because I'm tired. Right? So that's what that means.
What if you waterfall out of a can? Does that count?
Nope. I'm not going to drink it in a can because I heard that they found things inside of cans like rat bones and things like that. So I'm not gonna
Like, what if I poured in a cup?
Nope, I was still not drinking it. I need it from a bottle or a soda fountain, but I definitely need caffeine in it. Okay, Josue.
Are we gonna have these type of problems on tests?
Oh yeah?
What?
Yeah, not a lot. I mean, just a couple. But again, this is just using the vocabulary. This is important. We're seeing how to use the vocabulary to say something bigger. Okay. Now, hey, if this is your first time ever seeing this, we're still easing in, so don't worry yet. Just keep an open mind and just keep trying.
That's not good.
Don't worry yet.
Okay.
Trust me.
But we are definitely looking now at what we will be looking at, which is sets of real things, not just arbitrary sets of numbers and letters. We're looking at real things. Okay, so let's try this again. The lists below show 5 agricultural crops in Alabama, Arkansas, and Louisiana. Southern states, right? Are they all? They're not the southernmost states. Louisiana is, Alabama is, but Arkansas is what, right above one of them?
Yeah.
Okay, so mostly southern states. And so you can look through and you can see Alabama has soybeans, peanuts, corn, hay, wheat, and so on. We don't have to read it all. Now it says, let U be the smallest possible set that includes all the crops listed. So again now, U is the universe. U is the universe. It contains everything that you see up here. So that wouldn't hurt to write that down first. U is the universe from which all the other sets are constructed. So if I just write these letters down in somewhat of alphabetical order, well, it's kind of a pain, but I've got, let's see, C, H, P, S, and W from the first list. S is there, R is here, T is here, H is already listed, W is already listed, and then S is there, N is here, R is here, C, and T. Okay, so that's our universe. If you want to write it down again now, so it's nice and clean, our universe is C, H, N, P, R, S, T, W. Did everyone see how I came up with my universe list? I just started writing down the letters in alphabetical order, and I just filled in all the letters as I saw them. So that's the universe of all the crops grown in Alabama, Arkansas, Louisiana. So let U be the smallest possible set that includes all the crops, and then let A, K, and L be the sets of the 5 crops in Alabama, Arkansas, and Louisiana. So A is Alabama, K is Arkansas, and L is Louisiana. So now we just go look and see what these sets are. So for instance, A union K. So what is, I'm sorry, union, intersection. What does intersection mean again?
Well,
Oh, so what product is made by both Arkansas and Louisiana?
soybeans, peanuts, corn.
I don't see peanuts. We're
Just get it, wait, what?
wait, A and K. Sorry, not Arkansas, Alabama. Alabama and Arkansas. Jeez, I said that all wrong. That's Alabama and Arkansas. Yes, thank you. Go ahead.
So I was right.
Yeah, you're right.
Okay.
So soybeans,
Peanuts.
no.
Wait.
Yeah, soybeans.
What?
Soybeans for sure,
And wheat.
and wheat, and hay. Now, folks, there's a good way and a bad way to try to do this activity. And one is just to keep looking back and forth until you think you got it all. That's a bad way. A good way would be to start systematically at the top of one of the lists and just start writing and check. So S is, so I'm going to include S. P is not, so I won't write P. C is not, so I won't write C. H is, so I'll write H. And then W is, and then that's it. As soon as you're done checking one list, you don't have to go check the other one because you've already checked the first one. So by doing intersection, we're looking for anything that's in both, and so the only thing that Alabama and Arkansas produces in common is soybean, hay, and wheat. Right? Does that work? That's all they have in common? Okay, what about A and L? So that's Alabama and Louisiana, but this says union. So it's anything that either one of them makes. It's anything that I could order from Alabama or Louisiana. So again, you can start by just writing down everything that's in Alabama. So S, P, C, H, and W. Probably would have been helpful to write in alphabetical order. And now we just go to Louisiana and we write down anything else you see. So S is already there. N is not there yet. I'll include N. R is not there yet. I'll include R. C is there. And cotton is not there yet. I'll include T. So that's anything that you can order from either Alabama or Louisiana. Now again, don't you think that would have been easier if I had written the letters in alphabetical order? Probably, because then you can look and scan more easily. So if I did it in alphabetical order, so A, I'll write those in alphabetical order. So S, E, C, H, W. And then I'm going to sprinkle in anything else from Louisiana. S is there, N would be here, R is there, C is already there, T is not there yet. So there, now that's in alphabetical order. Schumpeter's. Okay. Questions about all that? We're building sets. The most important skill, what we're doing right now, is we're thinking carefully. But that's really what we're doing, is just we're thinking carefully about what to include and what not to include. Okay, so now we have some problems to solve. Jose is applying to college. He receives information on 6 different colleges. All of them, or any combination. How many possibilities are there for the set of colleges he applies to? We haven't done anything like this one yet. But the question is, he could apply to any of the 6.
What 6 are they?
College A, B, C, D, E, and F. A, B, C, D, E, and F. Yeah, so that's what we have. So our set of colleges that we're thinking about is A, B, C, D, E, and F.
So it's 3 answers?
What?
Is it 3 answers to the problem?
There's not 3 answers to the question. It's saying how many possibilities are there for the set of colleges that he applies to. So, for instance, he could apply to all of them. He could apply to none of them. That's 2 possibilities.
Oh.
Okay, we could go in a really nice order here and say, what if he applies to none of them? How many different ways can he apply to none of them? Just one. He just doesn't apply. How many ways can he apply to one of them? How many ways can he apply to just one college? He could just apply to A, just apply to B, just apply to C, just apply to D, just apply to E, just apply to E. So that's 6 ways. How many ways can he apply to 2 of them? Well, now this is going to be complicated because he could apply to AB or AC or AD or AE or AF, or he could apply to BC or BD or BE or DF, or he could apply to CD or CD or CF or DE to DAF or just EF.
36.
Was it 36? Did you count? As I said, it was 15?
I'll just do
It was
the dice.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I got 13.
David.
What?
That was
No.
David.
You got 15 as well?
Yeah.
Oh, no, I did that wrong. That was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, good. So there's 15. Now, who wants to count the next one? How many ways can he apply to just 3? And no, we don't even want to bother doing this because we have to proceed to ask how many ways can he apply to just 4 of them, and then to just 5, and then to all 6. So there's a lot of ways to count up to 3, a lot of ways to apply to 4 of them, a lot of ways to apply to just 5. But fortunately, there's only one way to apply to all 6. How many ways can you apply to all 6? Just one. You just apply to all 6. So we need to find what those numbers are. But this is what I'm doing right here is not the best method for solving this problem, because you'd have to sit there and come up with all these different ways that you can apply. So instead, what you do is you look at each one of these possibilities and you just say, yes or no, will he apply? So for each one of these colleges, you're just either going to say yes or no. Is he going to apply or not? And so this is a basic counting theory problem where you say, for each one of these colleges, he'll either apply or he won't. So that means how many choices does he have for college A? He will or he won't?
2.
2 options. College B, how many choices? He will or he won't?
2.
And so what you say is that for each of these colleges, you have 2 choices, and then you multiply all the way through the total number of possibilities. So you have 2, 4, 8, 16, 32, 64. There are 64 total ways. That's what these numbers would have added up to. There are 64 total ways to look at some combination of colleges. That might not sound very exciting. But keep in mind, this is actually the heads and tails problem. So if for instance, what if he only wanted to apply to 3 colleges, colleges A, B, or C? Then it's just like the flipping the quarter problem, where it's either heads or tails. You can call that yes or no. So either he doesn't, or 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 does, or does. So can you tell that the quarter problem for tails and heads would calculate the total number of ways to apply to some colleges? You could either apply to none, or you could apply to 1, or you could apply to 2, or you could apply to all 3. I don't know if that was very clear, but you can work it the same way. You're basically saying that whenever you flip a quarter, so let me do that. Here's your quarter 1, quarter 2, and quarter 3. You can flip a quarter. It's either going to be heads or tails, or it's going to be heads or tails, or it's going to be heads or tails. And that's 2 possibilities each. So you multiply them all together, 2, 4, 8. And how many ways can you flip a quarter 3 times? From the beginning of class? 8. 8. Yeah. Okay, so what we're looking at here then is this technique of buckets. And fortunately, the next problem is just like it. So let's look at this. Martina bought 5 books to bring on vacation. However, she decided that her bag was too heavy and that she wouldn't bring all of them. So how many possible subsets are there if she brings at least 1 book, but not all 5? So let's consider for each book. So we have 5 books. Everyone draw 1, 2, 3, 4, and 5. Those are 5 books. And in each case, she either brings it or she doesn't bring it. So there's 2 options, 2 options, 2 options, 2 options, 2 options. So how many different possible subsets are there where she either brings a book or she doesn't? That'd be 2, 4, 8, 16, 32. Because it's multiplicative. That's okay. So there's 32 possible sets of books that she brings with her. However, she said she wants to bring at least 1 book. So she's not going to bother with the set that says, no, don't bring it, no, don't bring it, no, don't bring it, no, don't bring it, no, don't bring it. We're not going to do that collection because she wants to bring a book. But she doesn't want to bring all 5, so she's not going to do the set either of yes, 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 yes. So that's 2 possibilities that we can ignore from the 32 possible. And so there are 30 different ways that she can choose at least 1 book, but not all, to bring with her.
Is there an equation for this?
Yes. The equation is you make buckets,
No.
you write down how many choices you have for each one, and then you multiply. No, really, this is called the fundamental counting principle. And the thing is, you just look at how many choices you have at each step, and then you multiply. Here's a nice example, everybody. Let's say you want to go to a restaurant. This is much nicer. And maybe I should have started with this. Maybe. So you go to a restaurant, and how many appetizers are there, Simone?
12.
Just 12, but make it a smaller number.
2.
3.
Great, 3. So there's 3 appetizers on the menu. How many entrees are there?
2.
Well, more than that.
5.
6.
Okay, 5.
7.
And then how many desserts do they have?
10.
3. 3 sounds good. Well, let's make it 4. Okay, so
What about
3
drinks?
choices. What?
Drinks.
And drinks. Which is probably 10. They have lots of drinks. Okay, fundamental counting principle. It states that if you have 3 choices of appetizers, 5 choices of entrees, 4 choices of desserts, and 10 choices of drinks, how many unique dining experiences can you have? Right? So it would just be 3 times 5 times 4 times 10. And that's how many totally different unique dining experiences you could have. Or maybe the appetizer, you have the bloomin' onion, and then you have the steak, and then you have the cheesecake, and then you have a RC. But then the next day, you have an onion, a steak, a cheesecake, and a Pepsi. Right? So these are 2 distinct dining experiences you could have. Let alone a completely distinct experience where you have, say, I don't know.
Watermelon.
Sure. A watermelon appetizer. And then you have the chicken, and then you have pie, and you have the RC. So the point is, if I actually sat there and wrote out all the different possibilities for meals that I could eat at that restaurant, it would end up being 3 times 5 times 4 times 10. Which is what? 3 times 5 is 15, times 4 is 60, times 10 is 600. So there are 600 different unique dining experiences that you can have at that restaurant.
And you always pick the same one.
Yeah, I know, exactly right. You always pick the same one. And we call this the fundamental.
Oh, it's time to go home, Simone.
Fundamental counting principle.
Literally.
Fundamental counting principle. So Simone, to answer your question, yes, there is a formula, and it's exactly that. You write out how many choices you have at each step, and then you just multiply them all together. And believe it or not, that's a wonderful formula.
No, it's something else. I know it is.
Well, there are other ones called permutations and combinations, and there are formulas for it.
Oh, that's probably one.
Yeah. Okay. Well, there we go, folks. That was set 7.1. So we might as well take our break because my phone just went off. So let's all come back together at 3:25.
Yeah, I'm good.
Yeah, so a lot of us do.
Ask, but it have to be that.
I can do it.
Yeah.
No, stop. Oh, I'm so mad. Okay. No,
There.
yeah.
Oh, yeah. I don't like that.
Really? Why not?
I got sick off for a long time.
Why? Like sick, like throwing up sick?
So stupid. Yeah, it's cool.
But then I was like, it's a whole process.
It doesn't sound.
Oh, really?
You do it anyway. It just goes away.
But not a lot of people say it.
They're easy to find the right ones.
Oh. Look at you. How old are you? 40? Because like every time I try to answer something,
How old are you?
21 and up. 19.
Well, Tama,
Yeah,
it's not common.
I know. I only know one person who has a job. Exactly.
then like when I did, I couldn't find like good ones. Like,
Oh, yeah.
Maybe, like,
But that's why the person I think they actually because like each one is like 25. There's nothing that has like just one. It's 100. Maybe the whole pack.
yeah, the whole pack would be like 400, but then it's like 20, like 10 milligram, like every so yeah, like
Yeah.
That's what I do for my friend's boss.
Mm-hmm.
He wants to do it for him. But he stopped it. My card expired. I was like, oh, it's expiring. It's like $400. It's like too much.
Dang, that's cool. I'm not saying that much.
But I mean, he owns his own business, so.
Yeah. Sorry to say.
Didn't have a bike. But gotta have a bike, gotta have a motorcycle. Yeah. She's living that one. Have you seen him before? Like, have you seen him? Do you know what he looks?
You gotta really catch up, child.
Have you? I don't know if he's older than me. I don't think he's gonna be younger.
I'm assuming they're like the same age.
Why is this one down?
And then you're younger.
I know she's talking.
Yeah. I'm staying for the next one. Guys, just wrong. Bobby's actually really smart.
Sean, Leslie, why you talking like that? Why you everyone is they are very excited. Why you being excited?
She independent.
know what are you doing? You're not a loser.
Oh, you still don't work? Don't work, start writing yesterday. They want to set schedule or different? What? They want to set schedule or is it going to change? No, set schedule. I'm getting 40 hours a week. Okay.
All right, folks, let's keep going. Where did our people go? Simone and Cheryl. Come on back, Simone, Cheryl. All right, so now, folks, we got something interesting here. These are called Venn diagrams. Have you all heard of Venn diagrams? Yeah. Venn, where does the word Venn come from? Van Helsing, that's funny, that was a vampire killer. But actually, yes, Venn is the name of a person. Venn is a mathematician who first did this. There's only in the 1800s. That's not very recent. I mean, that's not very long ago, I should say. Okay, so it says, shade the Venn diagram to represent the set. So what we're going to do, does everyone have these diagrams? Yeah. What we're going to do is when we represent one set, like set A, you're going to use horizontal lines, and if you shade set B, you're going to use vertical lines, because then we're going to look for the cross-hatching to mean that they were both shaded, okay? So let's try this first one first. So this is A complement intersect B complement. So let's do one at a time. What's A complement?
Not included.
Anything not in A. So anything at all that's not in A. So watch what I do here. I'm going to shade everything that's not in A. Did I do it?
Yeah.
I shaded everything that's not in A.
We're just doing the circle.
What?
I thought we were just doing the circles. We're doing the whole square.
Right, well, okay, so first of all, sorry. So this rectangle is the universe.
Yeah.
The rectangle is the universe. A is that circle, B is that circle, and you can see that there's some overlap between A and B.
Oh, man.
Okay, so now what about what's B prime? B prime is everything that's not in B. So now you need to very carefully shade everything that's not in B, which is going to be everything that's not in B. There, how do I do? Is that now everything that's not in B? Now what are they actually asking for? They're asking for A complement intersect B complement. And what does intersect mean again? Both. So that means what part is being cross-hatched? As in, you've got both vertical and horizontal. So what part is cross-hatched? The whole outside. Not A, because that's just one of them. Not in between, because that's neither of them. Not B, because that's just one of them. It's outside. And there's our answer. So I have the ability to erase, and maybe you do too if you draw lightly enough, but that's the answer for A prime intersect B prime. Yeah. Now we could make this, I suppose we could have started off with something easy. If we just wanted to look at, say, A intersect B, so this is A intersect B, where would A intersect B be? It means what's in both A and B? Just this little bit in the middle, right? So that's A intersect B. Is that fair? Whereas if I just wanted to know A union B, so again, here's A, here's B, and I want A union B, then that's anything that's in either. And so what would I shade? That. So yeah, those are two simple warm-up ones. That A intersect B would just be the part that's in both of them. And then A union B would be either A or B, or what they share in between. So those are two simple ones. Whereas the ones we're about to do are a little more complicated. So now what does this one say? This is B intersect A complement. So we won't do all of these, but let's do a couple. So first of all, B, so let's look at B. That's simply the circle B, so I'm going to shade that one horizontally. And then I want anything that's not an A. So anything not in A. So I'm going to do that one vertically. Anything not in A. There. And what we're wondering is intersect, which means both. B. So I need the parts that are shaded by both of them. So where's my cross hatching? B. Not all of B.
Part of B.
That. The quarter moon shaped part is cross-hatched by both of them. So that portion right there is B intersect A complement. And really, you can say it in words too. What we're looking at is for anything that's in B and outside of A. So that's what we're looking at, is shade the parts that are B and outside of A. And sure enough, it means I have to be shading anything in B, but I want it to be outside of A. So that's just that part right there. This next one, you'll notice is very similar to the one we just did, except now it's union. So shading B is easy. I'll start there. Shade B. So there's my B. And I want A outside of A. So I'm going to shade anything outside of A. So there's outside of A. And what I want is either. Anything that's either of them. So that means basically everything has some shading except for the moon of A. So I would end up leaving the moon of A unshaded, but then everything else is shaded. So have you all done Venn diagrams before? Maybe you have, maybe you haven't. It's a way of making a picture of what we're talking about in terms of the sets, so that you can do the calculation on the picture instead of writing it all out. So let's just do one of 24 or 25. Let's do 24. And you can cross out 25. So number 24, we're saying shade A, B, and anything outside of C. And then do anything that's not shaded by that. So this is kind of fun. Let's go in order. So A, I'm going to do horizontal shading for A. And then B, I'll do vertical shading. So there's B. And then I'm going to shade anything outside of C, because C complement means outside of C. So now I'm going to shade outside of C in blue. I don't know how you're going to do that. I'm going to do it in blue. So now I'm shading outside of C in blue. There we go. So far, I have shaded A intersect B intersect outside of C. So what part has shading from all three? Because we're looking for intersection. So what's in both A and B and outside of C? I want something in A and B and outside of C. First of all, A and B only intersect in this chunk right here. And what part also is shaded by C?
The top part.
Yeah, I'm sorry, outside of C. So it's just this little chunk right there. So far, that's what we have. That's what the inside of my parentheses is just A intersect, B intersect, C complement is just that little black section that I have right there. Out there means shade everything that's not that. And unfortunately, that is exactly why food and drinking, no, quickly, knock it off the keyboard. Yeah, dump the whole keyboard over. Just knock it over, get all the ice off. Quicker, dump it over. There you go. And then, I don't know what you want to do with the rest of that stuff, but I don't know if there are more electronics underneath.
No, I
Move everything. And if you leave your keyboard, turn it over.
That's the dad, Mr. Chief.
It's the what?
It's the dad you.
Yeah, well, let's see here. So that's turned upside down. You might want to go get a something. And then, well, see, it's all, that water's cooling down here and getting on all the electronics. And getting all over this. Everybody, move this whole table back. There we go. Okay, I think that's as far as we can go for now. The mouse is also covered. Alrighty. And then, who knows? We might move. All right.
Probably the best thing that happened in the day.
Okay, so let's keep going here. Now that last apostrophe says, now shade everything that's not that. So what are we really saying? We're going to shade everything in the world except for that little black spot. So now I can take away all of that I just did. I'll leave that little black spot empty, and I would shade everywhere else. So, yep, that's the answer. Now you might say, what's happening? What is happening? What are we doing? We're drawing pictures, we're shading things. But again, it's just very slow, careful thinking about what are we including in the set and what are we not including in the set. Okay, well, it's just a couple examples. Plus, how do you feel about that? Is it weird? It is weird.
I'm like really having a hard time.
I could go back and do that again slower. Like choose one of those that you want to see again. Or should we do that?
I'll look at 25. I'll look them over.
Yeah.
I mean, we get it. It's not clicking yet. So it's not you.
It's us. It's a combination of everything. It's me, it's you, it's the material. It's tricky. And to be fair, I mean, this isn't even the core thing. Well, we're going to practice it more as we go along. So I say, let's just keep going. We're building upon these concepts. Let's keep going.
Let's just take today out.
So, well, here, we have a couple examples here. These are some good ones. So, did you turn the page here on 26?
Yes.
All right. And I'll go a little slower here. Maybe I was going a little fast. So it says, use a Venn diagram to decide if a statement is true or false. So on the left, we have A intersect B complement, which means everything that's in A and not B. And on the right-hand side, we have not A or B, but outside of all that. Now again, this hurts the brain. This does hurt. This is challenging. So let's go very slowly here. The one on the left, we're going to make A intersect B complement. And on the one on the right, we're going to call A complement union B complement. Okay, so let's go very slow here. On the left-hand side, shade in all of A. Use vertical stripes, because that's A. There's A. And then also we're going to do B complement, which is anything outside of B. So anything outside of B. So I'm going to use horizontal stripes to do anything outside of B. So I'm going to shade in outside of B. Okay? And now what we're asking is intersection, what was in both? So what just got shaded by both vertical and horizontal? What portion?
A has some of it.
Yeah, the A moon shape right there, right? That shape right there got cross-hatching from both. Is that the only part that got cross-hatching from both?
Yes.
Yeah, that's the only part that got cross-hatching from both. So that's A intersect B complement.
Now, what would be the correct answer on the test? Just how would you want us to determine what's?
Well, we're not done yet.
Oh,
Now we need to negotiate this one and see if they're the same.
Okay.
Because they're basically saying, is that equal to that? Because that's a very complex formula right there. A intersect B complement equals A complement union B complement. So I mean, are those representing the same sets? So now let's do the second one. Now over here, we're going to do everything that's not A. So I'm going to do that vertically. I'm just making, whether it's vertical or horizontal, doesn't matter. So everything that's not A. So I'm going to do vertical stripes surrounding A. So there's not A. And then I'm going to do B with horizontal stripes. There we go. And union means shading everything except for the A moon, right? Because union means either. So I have shading everywhere except for the A moon. And now we're about to do the complement, which means where is everywhere except that has shading? So what's the only part that doesn't have shading?
A.
The A moon. So in fact, that is my answer. And the rest of that stuff would get erased. And in fact, is the left picture the same as the right picture?
yes.
Yeah. So in fact, this is a true equation. That is a true equation that A intersect B complement is equal to A complement union B complement. And the only way to do this is by just cross-hatching and shading and seeing how it works out. Obviously, Ms. Cheryl, we're most sad for the loss of your beverage. Okay. That's it. That's the only examples I want to do because we have a lot of other material in here. These are just drawing activities. Let it settle in. Go back and try 27 and go back and try 25. And of course, when you go try these problems online, they'll walk you through a video and show you another example of how to do it. So for now, let's keep going. And now we get to try it ourselves. Now, I admit those were kind of tricky. I think moving forward, you'll find that these are okay. Okay, everybody ready? We're at the bottom of that page. So number 28, at East Zone University, EZU, there are 628 total students taking college algebra or calculus. So first of all, everybody, the drawing that you're going to make is that you have two circles. You have college algebra or calculus. So I've got college algebra over here. I've got calculus over here. And theoretically, there could be some overlap where there are students who are in both college algebra and calculus. How that would work out, I'm not really sure if you're taking college algebra and taking calculus. But that's what we have so far. So what we know now is that there are 628 students taking college algebra or calculus. So that means that there are 628 students somewhere in those three parts. Right? So we're just saying that there's 628 students in either or both. It's just one or the other or both, because that's what or means. Or means that they're in one or the other or both. Now it says here that 278 are taking college algebra. So I'm going to use a little curly bracket to say college algebra itself is 278. And that 278 could include the portion in the middle. And there are 376 taking calculus. So just over here, that whole calculus circle is 376. And then finally, they're telling us that 26 are taking both. So now I actually know how many are in that little middle section there. So far, this is all we know, and this is what they've told us. And again, what are we doing? We're not doing algebra. We're not doing matrices. We're not even doing calculus. What are we doing? We're thinking very carefully about how many students are in each part of the Venn diagram. So does everyone agree so far with all the numbers that we've labeled? So we've got 628 students total in these different parts. 278 are just in the college algebra circle. 376 are just in the calculus circle. And 26 are strictly in the middle, taking both. So now, could we figure out how many are just taking college algebra?
Yes.
What would it be?
278 minus 26.
Yeah, 278 minus 26. That's how many people are just in college algebra. So we do 278 minus 26. And that'd be 252. So that's just right there. And then do we know how many people are just taking calculus, not both? Is that 376 minus 26? So is that 350? Now at this point, is our diagram completely consistent? Is everything that we have labeled here correctly? Is 252 plus 26 equal to 278?
Yeah.
Yeah, better be. I mean, we just subtracted it. And is 26 plus 350 equal to 376?
Mm-hmm.
Yeah, we just subtracted it. And then is all three of those add up to 628?
I hope.
Yeah, I sure hope so too. So if 252 plus 350 plus 26, that adds up to, whoop, I did my math wrong. Oh yeah, I just shouldn't have carried a 1. Yeah, it does add up to 628. Okay, so that's it. That's the end of the problem.
Nice.
How many are taking algebra but not calculus? So who's that? Where's the algebra but not calculus? That's those people, right? They're taking college algebra but not calculus. So how many? The answer is 252. Okay. So let's try another one. I think it's the same basic question. You got Eastern University, 510 taking college algebra or calculus. So I've got my Venn diagram. I've got 510 total split up between the 3 sections, the half minute on the left, the quarter minute on the right, and then the intersection in the middle. 320 are taking college algebra. So again, you want to label it college algebra, calculus. I've got 320 in this whole circle. And then I've got 224 in this whole circle. I've got 34 in the middle. So how do we do that again?
Subtract 34 from 224 and 320.
Yeah, you're subtracting it from both of them, right? Because you want to know how many are just those side sections. So 224 minus 34 would be 190. And 320 minus 34 would be 286. If I did my subtraction correctly. I suppose I better check. This is not a time to make a simple subtraction mistake. 320 minus 34. Yeah, 286 and 224 minus 34, 190. Okay, so is this diagram completely consistent? Is 286 plus 34 plus 190? Yeah, it adds up to 510. Okay, so how many are taking calculus but not algebra?
190.
Yeah, 190. So the answer is 190.
We're going to get questions like that on the test.
Sure. I mean, all of this is fair game at this point. But you all know, I appreciate your questions. You all know that I'll give you a practice test before the actual test. And I only take questions from the practice test to put on the real test. So, you know, that you can better inform yourself once you see the practice test. Okay, now we've got a really exciting one here. It says a survey of 280 families showed that 107 have a dog, 82 have a cat, 37 have a dog or a cat, and then 105 have neither a cat nor a dog, and did not have a parakeet. 9 had a cat, a dog, and a parakeet. And how many had a parakeet only? So at face value, I want you to notice that this question is crazy. Right? It's like, what? Like, this sounds like one of those logic game riddles that are in the newspaper, you know, or a game that you play on an airplane when you got like 5 hours. So let's start by making a Venn diagram. So how many different pets are there? So what you want to draw is you got your dog, your cat, and then you have a parakeet. So let's label it dog, cat, parakeet. Now, within this universe, keep in mind you draw a box around it, and you call that the universe. But probably the first thing I would do is just walk your way around the diagram and see if you understand what the different parts are. So like, who are these people?
Dog, cat, and parakeet?
Yeah, they have a dog, a cat, and a parakeet. Who are these people?
Just parakeet.
Just parakeet. Who are those people?
Parakeet and dog.
Yeah, they have a dog and a parakeet. Who are these people?
The universe. I mean, everybody. I don't know.
They're the people with no joy in their lives, right? Because they have no pets. Yeah, so you've got all these different sections, right? Okay, so this is dog and parakeet. This is parakeet and cat. This is dog and cat. This is only dog. This is only cat. This is only parakeet. This is all 3 pets. This is no pets. All right? So now what do we know? A survey of 280 families, that's how many people in the universe. We asked 280 people. Some of them have pets, some of them have no pets, but everybody, that's 280. Okay, so now 107 have a dog. So the 107 is split between that, and that. These 4 sections should add up to 107. So I'm just going to write dog as 107, because I know that when I add up all those sections in the circle called dog, better add up to 107.
Cool.
And then 82 had a cat. So now this circle with the cat, of that section, all 4 sections, those better all add up to 82, because that's how many people have a cat. So now cat I know is 82. Okay, then what? 37 had a dog and a cat.
So we'd put the 37 in the middle.
Right, and this is tricky. That includes this whole portion right here. Right, because this is the intersection of dog and cat. So these are all the people that have a dog and a cat. Some of them have a dog and a cat and no parakeet, and some of them have a dog and a cat and a parakeet. But on the way, that's 37. So we need to somehow label that in a way that makes sense. And honestly, what I would do right now is almost universally a good way to start a problem like this is to call the triple intersection point X. Like, because in fact, that's what they're going to ask us. How many, oh wait, they're going to ask us how many have parakeet only. But we can still go ahead and choose one of the sections to label as an unknown variable that we're going to solve for. Section, dog and a cat.
37.
37?
Wait.
So this would be 37 minus X. How does everyone feel about that?
Not too good.
That's 37 minus X.
My circle is too small.
Okay, but does that make sense why I called that the X and 37 minus X?
Yeah.
And actually, we might be able to fill that in if we just wait a second. Let's keep reading. Let's keep reading. 105 had neither a cat nor a dog and did not have a parakeet. So that's 105 people who had no pets at all, right? So we can go ahead and label that this whole space out here is 105. No pets. Which we should go ahead and do a quick subtraction. How many people did have pets? 280 people polled, minus 105. That means 175 have pets. Which means that everybody inside all these circle areas should add up to 175. Is that fair? Okay, we're still going to circle back to this 37 number, because I don't know if that's the best way to say it yet. But now 9 have a cat, a dog, and a parakeet. Oh, we'll go to gumdrops. That tells us that part. So if that's 9, then how much is that other part? It was 37 minus 9, because together they add up to 37. So is that 28?
Yeah.
Okay, well, there we go. Okay. Oh. A lot of times the best way to do this is just to keep on rereading over and over again and see if you've used all of your data. So have we used all of our data? I don't know yet. Also keep in mind, we don't have to solve everything in the world. We just have to answer the question. What's the question?
How many had a parakeet?
Yeah, so this question mark right here is all we need to find. It's just that. How many people just have a parakeet? Okay, so what should we do now? I would start back at the beginning and be like, okay, how am I going to get to there? So first of all, 107 have a dog. Now, we now know more. If 107 have a dog, do I know how much is in this moon shape?
Yeah.
I do. I know how much is in the moon shape now, because I can do, what, 107 minus 37?
Yeah.
So how much is in the moon shape? 107 minus 37? That's 70. So I now have 70 in that whole moon shape, which is going across both of those, this little section and that section, but that whole thing now is 70. Now what about cats? The whole thing of cats is 82, but that middle part is 37. So again, 82 minus 37, Now that whole part over there, all of that is 45. How does everyone feel about this? Okay, so 107 had a dog, we filled that in. 82 had a cat, filled that in. 37 in the middle, filled that in. 105 have neither a cat nor a dog or a parakeet, which means 105 don't have pets, which means 175 do have pets. And the last thing we want to know is how many just have a parakeet. Well, let's find out. Oh, did you already add that up? Oh, well, so first of all, we know that everything inside the circle region should add up to 175, right? Because those just inside the circles are people who have pets. So how many do we have so far? We've got 70 plus 28 plus 9 plus 45, which is 152, and 175 total. So we do, if that's 152, 175 minus 152 is 23. And that's it. Michelle, did that work? Okay. Okay, well, so again, what kind of math did we just do? It wasn't calculus, it wasn't algebra. It's honestly just careful thinking with the diagram, right? And it takes a while. It's kind of like doing puzzles, like I said, puzzles on an airplane or puzzles in a puzzle book. But there we go. Anyone want to ask any specific questions about that? Is there like one way to do this? Not really. I mean, you just kind of work the diagram. Wait, what was that, Simone?
Nothing.
Oh, yeah, you just work the diagram. So what I recommend you do now is just take out a separate sheet of paper and go back and try those again on your own and see how you would go about solving it. Because the way I just solved it might not be the way you might have solved it. But you just need to practice making a diagram and filling it out. Okay, well, I think that's it for Venn diagrams for a while. Now, as we proceed, we're looking at data and tables, and again, trying to think who's in the set, who's not in the set, and again, referring to the table. So take a look here. We're looking at H union A. So what does H represent? Well, let's read the whole thing. Given the following table, U.S. production in thousands of tons of certain nuts. So these are nuts made by the U.S. So the U.S. makes pecans, almonds, walnuts, and hazelnuts. So we want to know H union A. So H or A, either. So how many are in H?
40.
So find the number of elements in the indicated set by referring to the table. So the total production of hazelnuts over the last so many years. I wonder what the TFVS means. Doesn't really explain, does it? No, it sure doesn't. Well, let's just assume that they're saying total hazelnut production in all the time that's listed in the table. So either H, so that's all those guys, let's add them up. That means 9, 10, 11, 12, 16, 11, gosh. 122, I think. That's 122. We'll check the answer key in the back to see if we're interpreting this correctly. But I think they're wanting us to do all of it. Because they didn't tell us just one of those years, so I'm assuming it's all of them. And then, or almonds, which is all those. So I'm presuming that they're asking us to find the total production of all of these nuts. Find a number of elements in the indicated set. Yeah, it has to be. So let's add those up. 584 plus 584 plus 304 plus 412. That's 1884. And the other one was 41 plus 21 plus 39 plus 21. Yeah, that was 122. So between both of them, that gives us a total of 2006 tons. Let's check the answer key on that one and make sure that we read that correctly. The answer. It is the answer? Okay, good. So we did interpret it correctly. Yeah, they didn't give us any information to narrow down to just 1 year, so they must have been talking about all the years. And so that's it. That's all the nuts that were produced in either hazelnuts or almonds. So what you could do is you could say, in the years 93 to 96, 2006 tons of almonds and hazelnuts were produced. Same thing goes for the next one, but a little different. Now they're saying, oh, you know what? I bet these are different states. Vermont, Florida, Tennessee, South Dakota. All right, I mean, it could be states. Or Seattle. That's not a state.
It's a city.
Okay, so let's see what they're saying now. They're saying V intersect W. So V, we're talking about Vermont. Now look, this is fun. So these are all the nuts produced in Vermont, and we're looking at walnuts in Vermont. So how many were produced specifically walnuts in Vermont?
230.
Yeah, 230. So again, if you check the answer key in the back, it's going to be 230.
Oh, this is like too much.
Questions about that? Intersections. Okay, so when we look at unions on tables, unions, you're typically adding up entire rows or adding up entire columns. Whereas intersections, you're looking at the intersection of a row and column, which is partially why they call it an intersection. We're looking at the intersection of a row and a column, which is a single cell. Whereas a union, you're going to be adding up whole rows or whole columns. All right, welcome to Gumdrops. That's more or less it for all of that Venn diagram business. Now we're going to move on to just traditional probability questions. Boy, I feel like I need to let everyone take a quick nap, but we don't have time for that.
Maybe like 45 minutes.
Yeah, right. Or 45 minutes. Well, I tell you what, at 4:45, everyone can take a 48-hour nap.
Nice.
Okay, so let's give this a shot. Everybody, we're on to a new section. Everything that we just did, okay, section 7.1 and section 7.2. 7.1 was writing things down in set theory notation. Section 7.2 was using Venn diagrams. And now in section 7.3, we're moving into just regular old probability questions. So everyone, let's start. We'll start right here. It says, write the sample space for the given experiment. So again, sample space, if you want to underline it, write it down, is everything that could happen. As in, it's possible. So again, if you're rolling a die, you've got the numbers 1, 2, 3, 4, 5, 6. And an experiment, it's an experiment. You're going to do something. You're going to roll a dice. You're going to draw a card off of a deck. You're going to. So what's our sample space? First of all, a coin is tossed. So that's one event. And as you know, a coin being tossed, that's either heads or tails. But then you're going to roll a dice. And so that's 1, 2, 3, 4, 5, 6. And so we want to look at all the possible combinations of these things. And so what we end up doing is making a grid, just like the grid we saw at the beginning. Let me go back. Oop. There it is. We made this grid where you had dice on the left and dice along the top. Or in the cards, you had suits on the left and numbers along the top. So we're going to make a grid. And our grid will look like this. You're doing an experiment where first you flip a coin, then you roll a dice. So how many ways could that happen? You make a grid, and you're looking at heads or tails, and then rolling the numbers. 1, 2, 3, 4, 5, 6. And this is what could happen. You could flip a head, then roll a 1. Flip a head, then roll a 2. Flip a head, then roll a 3. Flip a head, then roll a 4. Flip a head and roll a 5. Flip a head and roll a 6. Or flip a tail and roll a 1. Flip a tail and roll a 2. Flip a tail and roll a 3. Flip a tail and roll a 4. Flip a tail and roll a 5. Flip a tail and roll a 6. And that grid is the sample space. Those are all the possible things that could have happened. How many possibilities are in our sample space? It's a 2x6 grid, so it's 12. There are 12 possible things in the sample space. Simone, how do you feel about that? Oh, good.
I really do think it's an easier way to do this. I'm just waiting for you to say it.
Okay.
Okay.
Magic. Okay, how about this next one? A box contains 3 blue cards numbered 1 through 3, 4 green cards numbered 1 through 4. Okay, that's all that's in there. A box contains 3 blue cards and 4 green cards. And they're asking, what's the sample space for picking a blue card and then a green card? So we could easily do the same exact thing we just did. You could create a grid. So you'd have 3 over here. So 3 blue cards, that could be blue 1, blue 2, blue 3. And then across the top, you could have green 1, green 2, green 3, green 4. Right? And then what they're saying is you're going to pick a blue card, and then you pick a green card. Now, this isn't hard. It's just monotonous, right, to write it all down. So what are all the possibilities for picking a blue card and then a green card? It'd be blue 1, green 1, blue 1, green 2, blue 1, green 3, blue 1, green 4. Unless you save the suspense, you know what would go in the rest of them, right? So how many different possibilities are there? 3 by 4, which is 12. So there's 12 different possibilities in the sample space. Now going back to the fundamental counting principle, remember if we just had a bucket, so the first thing you do is you pick a blue card, and the next thing you do is pick a green card. How many different blue cards are there? How many different blue cards are there? Yeah, 3 blue cards. And how many different green cards are there? 4. And so you multiply, and that's 12 different possibilities. As denoted by the 12 different possibilities inside the sample space. Okay. Write the indicated event and set notation. 3 coins are flipped, and more tails are obtained than heads. And all we want to do is just write down those. So if you want to look back at your list that you made at the beginning of class, we want to write down all the possible ways in which you can flip 3 coins, but you get more tails than heads. So that could either be just tails, or, going in order, a head and 2 tails, or a tail, head, tail, or a tail, tail, head. And I think that's it, right? That's the ways you can flip 3 coins and get more tails than heads. And that would be the sample space written in set theory notation. The next one, they were nice enough to give us the sample space. So take a look at that. That is the sample space. It says when 4 coins are tossed, exactly 3 tails are obtained. And when 4 coins are tossed, the following 16 outcomes are possible. So that's our sample space. These are all the different ways to flip a coin 4 times. And by the way, does it have the number that we expected? Remember before we said when you flip a coin 4 times, that's 1, 2, 3, 4 buckets. It's either heads or tails both times. So how many different possibilities were there? 2 times 2 is 4 times 2 is 8 times 2 is 16. There should be 16 ways to roll a coin 4 times. And how many ways do we have? 4 by 4 grid, so 16. So these are all 16 ways to flip a coin 4 times in a row. And the question is, when 4 coins are tossed, what's the probability that 3 tails are obtained? So go in there and circle every single one that has 3 tails.
Yeah, 16.
2 of them?
Wait.
That one? That one?
Oh, yeah.
That one? Is that right? Are those the only ones with 3?
The one next to it too.
No, yep, that one too. So there we go, we have 4.
Yeah.
So the sample space, what they're asking for would be just writing down set theory brackets for those 4. Now you'll notice these 4, they're pretty easy to list because you're just looking at either H in the first position, or H in the second position, or H in the third position, or H in the fourth position. So you can see that they're just basically cycling through which one of them is going to be ahead. So that makes the answer that there's 4 of them pretty obvious. Because if you have 3 tails, there's only one spot that could be ahead. Then it's just a matter of choosing where to put the H. So that would be your 4 options. I think that's all they wanted there. Write the indicated event and set notation. You would just list those out within the curly brackets, and that's it. Okay. We're ready to calculate some probabilities. I can tell you're all very excited. On the edge of your seat. So everything we've learned thus far, from set theories to Venn diagrams, it's all so that we can actually calculate probabilities. That's really the end goal of the whole chapter, is to calculate a probability. So first things first, everybody, go ahead and write down the definition of probability. So probability is a fraction. So first of all, it's fundamentally a fraction of, and this is how I always think about it, what you want to happen out of the total number of things that could happen. So want out of total, I think, is the fastest way to define probability. What you want to happen out of the total number of things that could happen. The more technical way would be the sample space is your denominator. That's all the things that could happen. And the desired event is the numerator. By the way, you're looking at how many ways can what you want happen divided by how many ways can things happen in general. We already did a couple of these in the warm-up. So in each probability problem, it's good to start by just writing P equals and a fraction. So a single fair die is rolled. So first of all, how many ways can you roll a die? 6. And they're saying the desired, what they want, is to get a 3 or a 6. And so there's 2 ways to do that, to get a 3 or a 6. And the answer is up there. Now keep in mind the answer key is going to give, the answer key will normally give answers as fractions. If you check the back right now, what does it say? Does it say a third or does it say 0.3333?
1/3.
Yeah. So our answers are typically going to be fractions, but every once in a while they could give an answer as a decimal. Okay, so again, number 38. A single fair die is rolled. The sample space, there are 6 possibilities. And now it says the number on the die is not 6.
So
5 over 6.
Yeah, so 5 over 6. A single die is rolled. The number on the die is less than 6.
5 over 6.
Yeah, still 5 over 6. Now some of these you can do in your head, but other times it's still helpful to write out your sample space. Like I would just write out the numbers 1, 2, 3, 4, 5, 6. That's my sample space. And I want a number less than 6, so I'd say that one, that one, that one, that one, that one. And I'd count them up, and there's 5 of them. So the circled ones are what I want to happen. All of them are what could happen. And then for the probability is 5, 6. So probability is 1 over total.
That is so.
Now, in your photocopied packets, did I give you the sample space of the dice?
No.
I kind of don't think I did. So let's see, do I have it? No, it's all the way at the back. Well, that's fun. Okay, I want to put my sample space somewhere that I can more easily get to. So when you go home, you can just do sample space 2 dice. And there we go. There, I like that one. Can we make it bigger? That's not very big. It's a little bigger.
Too big.
Good. Yeah, maybe a little. There. Okay, so what's our first question?
4 dice are rolled, the sum of the numbers on the dice is 4.
Yeah, so which one of those adds up to 4? Oh. Which one of these pairs adds up to 4?
3 and 1.
Yeah, 3 and 1. 2
Yeah.
and 2.
1 and 3.
1 and 3. So you'll notice, first of all, the same sum ends up on a diagonal. So like which ones add up to 7? 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. So the sums are always on a diagonal. So which ones add up to 4? 2 and 1? I'm sorry. 3 and 1, 2 and 2, 1 and 3. How many are there? 3 out of 36.
112.
So the probability would be 3 out of 36, yeah, which is 112. 2 fair dice are rolled. The sum of the numbers is 1 or 5. Yeah.
5.
Oh, okay, Bata. 2 fair dice are rolled. So these are all the different ways you can roll 2 dice. And it says, what is the probability? They're asking, what is the probability that the sum of the numbers is 4? Meaning that the 2 dice add up to 4. So look, here, 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. So it's that, and that. That's 3 possibilities. Whereas like here, 3 plus 3 is 6. That's not what we're looking for. Okay. Okay, so folks, the sum of the numbers on the dice is 1 or 5. So first of all, can the dice add up to 1?
No.
No. Can they add up to 5?
Yes.
Yeah, 4 plus 1, 3 plus 2, 2 plus 3, and 1 plus 4.
What?
So that's 436. That's 4 possibilities out of 36, which is 1 dice. Okay, what about 2 fair dice are rolled? The sum of the numbers is greater than 10.
Ooh.
So first of all, greater than 10. Do we include 10?
No.
No, just greater than 10. So here's 10, 6 and 4, 5 and 5, 4 and 6. So how many are greater than 10?
3.
Yeah, those guys down there. So you've got 5 and 6 is 11, 5 and 6 is 11, 6 and 6 is 12. So you've got 3 events where the sum is greater than 10. So that would be 3 out of 36. Which simplifies to 112. Banta, does that make sense? What?
Yes, but and how can we come to the 3 over 36?
Right, because first of all, how many total ways are there to roll the dice? You've got 1, 2, 3, 4, 5, 6, and then across 1, 2, 3, 4, 5, 6. So 6 times 6 is 36. You've got 36 possible rolls of the dice. So that's the denominator. In any probability problem, you want 1 out of total. The total is 36. Yeah. Does that answer your question? Okay. Yeah. Whereas what you want to happen are these specific things that we're looking at. Like I want to roll a sum greater than 10. So that means I want this, this, or this. There's only 3 of those that I want to happen. So the probability is 3 out of 36, which reduces to 112. Okay. Okay. All right, and then we also have problems about dice. So let's see here. Now I'm going to go back and do sample space cards. Oh, sorry, cards, not dice. I already said. So here's a, there you go. Nice one. Oop. There. So our next question is, when a single card is drawn from a well-shuffled 52-card deck, find the probability of getting a red card. So let me be more specific here about where'd my blue red go? Oh, all the way over here. So using this formula of 1 out of total, what do we want to happen? That's 13 times 2 is 26. Whereas the total is the total number of cards in the deck was 52. And then when you reduce that, it's 1/2. Of course, just looking at the grid, you know it's 1/2. Because half of the numbers are red and half of the numbers are black. So that's the probability of getting a red card. The next one, when a single card is drawn from a deck, find the probability of getting a 7. So how many 7s are there? Yeah, so that's what you want to happen. So your probability now, 1 out of total, what you want to happen, there are 4 7s out of 52 total possible cards you can draw from. And that simplifies to 1 in 13. Simone, how's that? Close way?
Those are easy.
Oh, okay, very good. Luis? All right. The next few problems are, well, they're a variety of different things. Let's do the card one, and then I'll get rid of it. When a single card is drawn, find the probability of getting a club. So how many clubs are there?
13.
Yeah, so we have 13 out of 52. Which simplifies to 1/4, which again is kind of obvious because clubs is 1 out of 4 suits. So the probability is 1 out of 4. Okay. But do you have any questions? Okay. Diego? No. David? Sarai? Sadia? All right. So one thing that's very helpful when you do probability problems is to draw out your sample space. We've already been doing that, but drawing your sample space is helpful. So a bag contains 3 red marbles, 8 blue marbles, and 7 green marbles. What's the probability that a randomly selected marble is blue? So at the very least, you could draw yourself a bag and write 3 red, 8 blue, 7 green. You can be even more specific and actually write out like red, 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 blue, 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 blue. But I'm imagining you'd get pretty tired of doing that. And then green, 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 green. So that would be a nice picture of my sample space because I can literally see every single marble in the bag. But this is probably fine. So what's the probability that a randomly selected marble is blue? So again, you'd say probability is 1 over total. And what do you want? A blue. And how many blues are there? 8. And the total is 7 and 3 is 10 plus 8 is 18. So our probability is just 4/9. Same thing in the next problem. You have a bag containing 8 red, or red down, 2 blue, and 1 green. What's the probability that a random marble is not blue? Well, that's a fun one. Probability is 1 over total. The total we can see, 8, 2 is 10, 1 is 11. And then how many are not blue? Yeah, if you just cover up the blue and take a look, you've got 9 that are not blue. So that's 9 out of 11. Okay, 48. Have you guys, you know what we're talking about with a spinner? What's a spinner? You got like a little thing with an arrow on it. You flick it with your finger and then it spins around and around and stops somewhere randomly. So a spinner has equal regions numbered 1 through 21. Can we draw a picture of that? Probably not so much. 21 regions. It's a lot of regions. How does that look? Does that look like 21 regions? We're just pretending anyway, right? So that's 1, 2, 3, 4, 5, dot, 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 all the way up to 19, 20, 21. Oops. Sorry. 19, 20, 21. Okay, so can everyone imagine that you've got the spinner completely labeled? What's the probability that the spinner will stop on an even number or a multiple of 3? This one's actually a little tricky. So what are your numbers that are even or a multiple of 3? So just imagine you've got money on this, right? You're gambling money. And if you can spin an even or a multiple of 3, you'll win $1. A whole dollar. So how many numbers on this spinner are even or multiples of 3? Everybody, I'll start by writing it out. What numbers are even?
2,
2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Is that it? And then how many are multiples of 3? 3, 6 is already mentioned. 9, 12 is already mentioned. 15, 18 is already mentioned. 21. So those are all the numbers that are either even or a multiple of 3. And so what we want to happen is any one of those. So it's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Did everyone else get 14? And what was the total? 21. So that's simplifying 2/3. So that means you'd have a 2/3 chance of winning that game, or 0.7 or 0.67. Now, did you notice how we did it set theory right there? We listed all the numbers in the set of even numbers, and then we did all the numbers that are multiples of 3, which some of them were listed twice, so we only counted them once. Okay. All right. We're moving along here, folks. We're getting into more and more sophisticated problems. Problem number 49. Each of 10 tickets is marked with a different number 1 through 10 and put in a box. If you draw a ticket at random, what's the probability that you'll draw a 3, a 4, or a 1? So 1 down a total. What would it be? Yeah, 3 out of 10. What you want to happen is to get a 3, 4, or 1. That's 3 different ways that could happen, and total is 10 cards, and so it's just 3 out of 10. Luis, how's this? Question? Okay. Okay, so going back to data tables here, find the indicated probability. The age distribution of students at a community college is given below. So let's look here what the table says. There are 412 students who are under 21. There are 412 students who are between 21 and 25. 213 students between 26 and 30, 60 between 31 and 35, and 26 over 35. How many total students are there?
1,120.
Thanks, Simone. And that's our total, obviously. That's what we'll use in our probability computations. So a student from the community college is selected at random. Find the probability that the student is at least 31. So at least 31. That means 31 or older. So who are we interested in?
31 and up.
Now, all those people. Right? So our probability then is going to be what we want out of total. And what we want is that there are 31 to 35 or over 35, so that's 60 plus 26. And of the total, which is 1, 1, 2, 3. Does that work?
86 over 1,000.
Mm-hmm. I think you type that in your calculator. So 86 out of 1, 1, 2, 3. Okay. The next one's pretty similar. It says this is a distribution of Bachelor of Arts degrees conferred by a local college. What's the probability that a randomly selected degree is in chemistry or physics? So what do we want? So again, we're doing 1 out of total. We want people that are either chemistry or physics, so 318 plus 856. And the total they gave us was 9313.
It's 318, not 315.
Oh, 3.
8.
Yeah, thank you.
Yeah.
All right. Okay, whatever that is. Somebody already added all together.
1,174.
Okay, so 318 plus 856, 1174 over 9313, which turns out to be 0.126. And they did ask for 3 decimals of accuracy, right? Yeah, 3 decimals. So just over 12%. All right, this next one is a little more interesting. They're saying college students were given 3 choices of pizza toppings and asked to choose one favorite. The following table shows the results. Find the probability that a randomly selected student prefers cheese. So we have a little work to do here. How do we do this?
Add up cheese.
Right, out of all the cheese. So first of all, probability is 1 out of total. And what we want is the total number of people who like cheese. So yeah, we'd have to add up all those cheese responses. Did anyone get 72? Yeah, add them all up. So since we already added one row, it makes sense to just add the other rows.
220.
So this row is 72, this row is 74, and then the next row, 13. I believe you see my finishing the class. So those were the 3 row columns, then 72 plus 74 plus 74. I think it's 220.
Thank you.
So then we have 72 divided by 220, and again, they want 3 decimals of accuracy, and it's 0.327272727. Yeah, so it stays that way. So about 1 in 3 people, right? Simone, are you okay? I thought you were choking. All right. Okay, moving on in here, folks. We might not solve it completely, but let's talk about how we would solve each problem. Because we still have a few more types to get to. Yes, we still have a lot left to get to. And we'll just see how far we get. This might go into next class period a little bit.
Oh, you're going to say cross them all.
Yeah. Okay. So the next one, it says, find the probability that a randomly selected junior prefers meat. So who are we just interested in?
Juniors.
Juniors that like meat. And so how many are there? Just the 11, right? So this is an intersection problem. We're looking at just juniors who prefer meat, so we're looking at 11 out of whatever the total is. So we don't have to add them all up. It's enough for us just to look at these problems and notice what we're trying to calculate. Okay, about the next one. The following table shows the grades of college students in an advanced math course broken down by year. Use the table to find the probability that a randomly selected sophomore gets a B. So what we want is a sophomore that gets a B. And so how many sophomores got a B? 4. Yeah, 4. So that's it. And we know the total number of students, because they gave it to us, is 100. Now actually, I take that back. That 100 is a percent. And that 100 is also a percent. So we would actually have to check to see how many total students there are. And if you either add up all the rows or add up all the columns, that would tell you how many students there are. I wonder if it's actually 100. I think it is.
Would you?
Because these are numbers of students. So if you look at all this, each row and add them up, what did you get?
So what's the percentage of it? It says 423. Yeah, and the answer.
Oh, okay, so hold on a second.
Look at the sophomore.
Find the probability that a randomly selected sophomore gets a B. Okay, thank you. Let's slow down a second here. We're saying, look at just sophomores. What's the probability that a sophomore gets a B? So we're only looking at sophomores. Oops. So when we think about 1 out of total, in this particular problem, thank you for saying what the answer was. So I slowed down. We're saying find the probability that a randomly selected sophomore. So that's the only people we're looking at is just the sophomores. And what are we saying about them? That they got a B. So the total number of sophomores is 23. And what we want is a sophomore who gets a B, which is the 4. Does that make sense?
For the first one, do the same thing, 28, is that right?
Find the probability that a randomly selected junior prefers meat. Thank you. I was going too fast. I'm very sorry, folks. Yeah, we want a randomly selected junior, so we're looking at just these people. And we want that they like meat. So that would be 11 who liked meat out of the 28 plus 11 plus 21. I'm very sorry. I was getting ahead of myself. So 28 plus 11 plus 21. Was that 11 out of 60?
Yeah.
Okay. Sorry, yeah, these problems got a little more subtle. because they're narrowing they're asking us to narrow our field of vision, not just everybody, but just certain groups of people. Well, good. Let's do this last one correct. Number 55. This shows the popular votes in 1984 by region, so that's Northeast, North, Midwest, Southwest, and by party, so Democrat, Republican, other. A person who voted Republican is selected at random. So first of all, we're only looking at people who voted Republican. So we're only looking at this column right here. Find the probability that that person was from the Midwest. So that's what we would need. Is we're only looking at Republicans, so that total, so 1 out of total. We're only looking at Republicans, so that's the total is 5, 4, 4, 5, 5. But we're only wanting people from the Midwest, so that's 14,761. Does that make sense?
Don't we put it over the entire total?
Well, but they're saying a person who voted Republican is chosen at random. So they're only choosing from Republicans. That's why it's not over the total. You're just doing the total of Republicans. Does that answer your question, Simone?
Yeah, it does.
Okay, section 7.4. So we just finished a whole bunch of probability problems. And these are going to be slightly more sophisticated probability problems. Now, let's take a moment here. We've got section 7.4, and then section 7.5, and then Bayes' theorem. Okay, so three more sections, and I suppose if you just go by number, we're a little over halfway, right? Yeah, we're a little over halfway. What's the probability that we're a little over halfway? Yeah, that's okay. You know, we get as far as we'll get.
We can always cancel the final and then just move everything.
Yeah, right. Yeah, yeah. So you know, I might choose to get rid of some of these, but right now my thought is we'll just flow this over to the next class period. So let's just keep on trying sample problems, and we'll see what happens. Because what the class ends at 45.
Yeah, we got like 10
No,
minutes
it like
to cram
at
it
like
out.
4:40, like 6:40.
Yeah, no, we're not going to rush. We won't. No, class gets out at 4:40.
Yeah,
4:50?
45.
Okay, 4:50. Yeah, we won't cram it. Wait, what about that? No, I didn't hear you. All right, let's just keep going along. So, this next section is about whether or not events are mutually exclusive. So, events that are mutually exclusive on a Venn diagram would be events that have no overlap. No overlap. Meaning they don't affect each other at all. So just to give you an example of mutual exclusivity, well, I mean, all of these are examples, so we can just walk through them. But a good mutually exclusive event would be roll a die and then roll another die. Does what you rolled on the first die have an influence on what you roll next? No, because the rolls are independent. So those events are mutually exclusive. But now let's say I have a card game. And in my card game, so here's a deck of cards. The game is that you just draw one card off the top, and if you get an ace, you win 50 bucks. Now, the first person drew a card, and they got an ace. Now you are about to draw a card. Did that person's draw have an effect on what you could get?
Yeah.
Yeah, because there were four aces in the deck, but now that they drew one, now there's only 3 aces in the deck. So drawing cards off the top, that's not mutually exclusive, because every card that you remove from the deck is affecting what the next person could draw. So let's look at these examples. So determine if these are mutually exclusive. So you obtain a spade and then obtain an ace when a single card is selected from a deck of cards. So is it mutually exclusive about a card being a spade and being an ace? Well, that's really not the best example.
You're getting one card, but you're getting.
It's when a single card is selected from the deck. And in fact,
spades, is that what you're saying?
Yeah, they're basically saying if you draw an ace of spades, is it exclusive whether or not you can get a spade and an ace, and does that have any effect on each other? Ooh, I really don't like that question. I'm taking a face card and I'm taking a 2.
We'll just skip 7.4.
Well, no, we're not going to do that. Okay, let's hold off on this one. First of all, is it possible to get a spade that's an ace?
Yes.
Yeah. What about this next one? Is it possible to get a face card that's a 2?
No.
No, because face card is a jack, king, or a queen. So just so everyone knows, a face card is a jack, a queen, or a king. So obtaining a face card and getting a 2 when a single card is drawn, you can't draw a card that's a jack, queen, king, and a 2. So that's not even possible. This one's not even possible. Likewise, this next one, can you be a male and a nurse?
Yeah.
Of course you can. That's possible. And the next one, can you be a teenager and a senator?
No.
No, because you have to be 35, right, to be a senator? Is it 35?
For 57, they have yes.
Hmm?
In the answer key for 57, it says yes.
Oh, okay, well, I'm sorry. That's correct answering their question. Are they mutually exclusive? Yes, they're mutually exclusive because they can't both happen. So mutually exclusive means they can't both happen. So are they mutually exclusive? Yes, they can't both happen. So thank you, Josue. Yes. Which is another way of saying what we said. So yes. They are exclusive because they can't both happen. Is being a male and being a nurse mutually exclusive? No. You could be a male nurse. Okay, this makes a lot more sense about what they're asking. And then finally, can you be a teenager and a senator? No. You can't be both. Well,
It's mutually.
yes, it's mutually exclusive. You can't be both.
Are we required to know like the background information and that stuff? Because I don't know.
Yeah, that's a good point.
Because they're gonna ask questions like that.
Yeah, certain things that you would need to know, huh? Okay. Now, but the first question now, going back to that, is it mutually exclusive that you can you be both a spade and an ace? Yes, you can be both. So are they mutually exclusive? No. You can be both an ace and a spade. Yeah. Okay. Well, my phone just went off, so I have to make some choices here. What I'll do is I'm going to go through the rest of the packet, which is about 40 problems, and just choose the ones that I really, really like, the ones that I like the most. And so that's what we'll do at the beginning of next class on Thursday. So what I would do if I were you folks is I would go home tonight and work on the homework 7.1 through 7.3. So for sure, you can start your homework of 7.1 through 7.3. And then next Thursday, we'll finish 7.4 through 7.6. And I'll just choose select problems from there, and then you won't have to do all of them with just someone. Okay? So I tell you what, I'm not ending class early because I still want to pass out your tests. And these are just a couple minutes for anybody who wants to ask questions. Look at your test, ask me questions about that, ask me questions about the material. There you go. Oh, me sure all that. Josue. Luis. Marta.
What is this?
You're welcome. Simone. David.
Graded my test one. I'm just kidding.
Diego.
No.
All right, anybody ask questions? Come on up, ask me. Why is this just 20 minutes to do whatever you need to do? Just what you guys are telling me is I included too many practice problems in this one, right? I included too many practice
Oh, this
problems.
packet? It's like a book.
Yeah, it is like a lot.
It's like a pack wheel. I mean, it's good though.
No.
Because then we get to learn more, but-
Yeah.
Our knowledge grows.
But then if you wait till the
You're trying to kiss.
That'd be a
Oh,
problem.
hold on, so where's my car key? Almost. I'm walking home.
I'll take an 86 though. That's cool. We should test practice.
Do you know what the actual number for this problem?
Where's number 4?
Yeah, that's you're just supposed to set up.
Oh, yeah, let me show you a really cool tool.
Actually, I used the one that you saw on the website.
Yeah.
But it has all kinds of other like symbols and letters.
It does.
I don't know which one to answer.
Yeah, I can show you the answer. This is the actual test, right?